good morning, everyone. Thank you very much for the kind introduction, and many thanks for the kind invitation. So it's an honor for me to be here. It's my first time in Portugal. I'm very glad to be here. Thank you. So I'm going to talk about digital twins for optimizing battery manufacturing processes. And first of all, I will say a few words about the lab I'm working, where we are locating, what we are doing. So I'm working in the lab called Energy Lab, which is the headquarters of the French network on electrotechnical energy storage, which is a network getting together something like 30 academic labs and 30 companies in France working on the battery field. So we are located in the city of Amiens. Amiens is about 1 hour by train from Paris in the north. And we are about 140 people working mostly in battery technologies, including lithium-ion batteries, sodium-ion batteries, solid-state batteries. And we are located in the so-called French lithium-ion battery manufacturing valley, battery manufacturing valley, because in our region we are hosting the 4 battery gigafactories located in France. One of them is already a reality, the one of ACC is already operating and producing batteries for automotive applications, for cars. Others are under construction. So therefore, this is a very nice environment to work in the field of battery manufacturing. Right? And what I would like to say first of all is that producing batteries, manufacturing batteries is complex because you have multiple steps which are interconnected with each other. You have many parameters that you need to handle, you need to optimize in order to get batteries that they perform well. Therefore, this is a very complex optimization problem. Right? And if you optimize the battery manufacturing process based only on trial and error, you will have very high scrap rates in battery production. These scrap rates, they can be as high as 5% when you are producing batteries, for instance, in a gigafactory, and they can be as high as 30% when you are prototyping batteries. That means when you are trying to scale up a battery concept from the lab to the factory, right? Because you are changing a lot these manufacturing parameters to try to find the optimal manufacturing conditions to then go to mass production. So this is the problem that we are working essentially in my group. So in my group, I'm leading a group of 25 people doing both things, modeling, but also doing experiments. And that's why, because of the complexity of this battery manufacturing optimization problem, that's why the concept of digital twin started to emerge, in particular in Europe, since a few years ago. And the idea here is that you have the real factory, producing the electrons that you have in the, for instance, lithium-ion batteries, producing the battery cells and so on. You have sensors in the machines, producing, for instance, the electrodes, measuring the thickness of the electrodes, the homogeneity of the electrodes, and so on, and then sending this data into a model, right, that is running in a computer, that is going to perform on-the-fly optimization of the manufacturing process. And then this model is going to provide via actuators instructions to the machines to allow the machines to improve autonomously the production process, to improve the quality of the electrodes being manufactured or the performance of the cell being manufactured in an autonomous fashion. This is a vision that doesn't exist yet, but this is actually providing the guidelines, right, where we should go in terms of digitalization in battery manufacturing to allow improving the quality of the electrodes and cells being produced, and in order to also reduce the scrap rates. If you are talking about this concept, for sure, it's like saying, okay, the machines are robots, and the models is actually a brain of the robot, right? And if we are talking about a problem with many parameters to optimize and so on, of course, AI seems to be the appropriate tool to handle this kind of optimization problem, which is a multidimensional optimization problem, right? Now the question is AI available to address battery manufacturing problems? These are a couple of reviews that we wrote a few years ago. And basically this situation was the following. So AI was already applied for battery problems, for solving battery problems, but not for manufacturing. Mostly it was applied for discovering materials, for instance, active materials that we put inside electrodes in lithium-ion batteries, for instance, to discover electrolyte materials. That was also another component which is essential for battery operation. AI was also applied to analyze images arising, for instance, from microscopy or computer tomography to understand how the materials are organized in space, or how the interface look like inside electrodes in the lithium-ion battery cells. And AI was also mostly applied to predict the lifetime of battery cells, right? But nothing about manufacturing, nothing about manufacturing. Now the question is, do we have enough, for doing AI we need data, right? And I think everyone here in the audience knows that, right? Without data, you don't have any AI is not possible, right? And the question is, do we have data available in relation to battery manufacturing, right? These are a couple of studies that we report based on text mining. So we have screened a lot of papers dealing with lithium-ion batteries, sodium-ion batteries. And actually we realized that we are in the battery field facing a kind of data problem, because there is a lack of standards in the way of reporting data in scientific publications, for instance. We realized that, for instance, you can see here, 97% of the papers, they don't report electroporosity. And this is a property which is essential to report in order to allow peers to reproduce an experiment, and also to have data that can be used afterwards in a useful way in an AI platform, for instance. We also found that 90% of papers don't report electrode thickness, right? And so on and so forth. Therefore, this is a problem. The battery data available in literature is not useful to handle battery manufacturing problems. Therefore, what you need to do is you need to produce data in-house. But to produce data in-house, you need a factory. You need actually machines that will mimic how batteries are manufactured in industry. Okay? You cannot produce batteries by hand, right? Because you will have too high variability of parameters in that scenario. And this is why I imagine an initiative, quite artistic. This is actually an initiative that was funded, as it was mentioned by the chair, twice by the ERC. And in this initiative, so basically what we wanted to develop is a digital twin of the battery manufacturing process, in particular for lithium-ion batteries, lithium-ion battery cells. And this initiative, this digital twin, is highly supported by data arising from a pilot line that we have in our lab. So we are very lucky because we have a small factory in our lab producing electrodes, producing cells. Therefore, we can produce high-quality data in enough amount to feed into our digital twin to validate it, and so on and so forth. This digital twin is supported on two pillars. We have actually a first pillar which is based on physics-based numerical simulations, able to simulate each step of the manufacturing process of the electrodes and the battery cells, and producing, for instance, 3D virtual representations of the electron microstructures. And the second pillar is based on machine learning, able to unravel correlations between manufacturing parameters and the properties of the battery cells that we want to optimize. An example of properties that we want to optimize is, for instance, the battery autonomy, so how long the battery will live, right, to power a device, like, for instance, an electric car. And the durability can be also another property that we want to optimize, and so on and so forth. Okay? And again, here these pillars are fed with the data that we acquired in this pilot line that we have in our lab, which mimics how we manufacture lithium-ion battery cells in industry. We have published a lot of papers, as you can see there, in this field. So today I'm going to share with you some highlights. I will focus mostly on our latest publications in this regard. One of the major deliverables of this artistic initiative is a platform, a software platform, able to perform inverse design. And as you will see, AI here plays a major role to achieve this idea or this concept. So first of all, in this platform, so we have these physics-based models, which are numerical models, classical models, simulating each step of the manufacturing process and able to predict, for instance, 3D resolved electron microstructures. So these models are calibrated, validated with the data that we acquired with our pilot line, as I mentioned before. Then, so what we do is we build data sets which are hybrid, which actually include at the same time experimental data, but also synthetic data produced by these physics-based numerical models. Then on top of these data sets, so we apply a batch of AI techniques in order to unravel correlations between manufacturing parameters and the properties that we want to optimize. These correlations, they look more like surrogate models. It's more like algebraic equations linking the manufacturing parameters X with the properties that we want to optimize Y. Manufacturing parameters here, examples of them could be the drying rate of your slurry, the formulation of the slurry, the pressure that you apply in the calendaring step, and so on and so forth. And the properties that we want to optimize, once again, can be the autonomy of the battery, the so-called capacity. It can be the energy density, that means the amount of energy that you can store per unit of volume or unit of weight in your battery cell, and so on and so forth. Once you get these survey models, which are actually, computationally speaking, very cheap, because basically you put a number and almost instantaneously you get the response, in contrast to the physics-based models that are heavy, computationally speaking, because to run this pipeline here, so it will take you something like a few hours to a couple of days. Once you get these very high speed models, you can embed them in a Bayesian optimizer that will basically predict which manufacturing parameter values you need to adopt in order to maximize or minimize the site properties for your electrodes and for your cells. For instance, you want to maximize the energy density of your cell. This tool will predict all the possible manufacturing recipes that you can adopt in order to reach your site target. And this is actually a fantastic capability, so much needed by industry. Industry really wants to optimize faster, battery cells and so on. And they want actually to know which manufacturing parameters they need to adopt in order to basically improve the, let's say, durability, for instance, of the cell that they are producing. Right? With this platform, this is possible, but it's possible because we are combining all these pieces all together. That means physics-based simulations with high-quality data, with AI, and with inverse design tools, for instance, based on Bayesian optimization. Now, let me show you the different components, of this platform a bit in detail. And I will start here with the physics-based simulations, right, which are in the core of this strategy and this concept. So these physics-based simulations, they are simulating the manufacturing process at the mesoscale, which is a new way of looking on this problem that we have introduced in 2017 for the first time in Journal of Physical Chemistry Letters. Basically, here we are using a collection of MD, molecular dynamics-like tools, which are actually not resolving the interaction between molecules. Here, what we resolve is the interaction between particles, at the mesoscale. So these particles here, they have micrometer size, okay? So the models actually simulate the slurry, which is actually a ink, where you have a suspension of the active material, the carbon, the binder, which are the essential components, the essential materials you have in the electrode. These particles and these materials are in suspension in a solvent. Then we simulate the drying process. Then the electrode is formed, the microstructure in 3D then can be watched in the computer. Then we simulate the calendering. The calendering is the step where you need to press the electrodes in order to improve the electrical contact between the particles, because a battery is dealing with handling electrons, and therefore the electrodes, they have to have good electrical conductivity. That's why you use to press the electrodes with a machine called the calendering machine. Well, this is something that we also simulate, and at the end, so you get a virtual 3D representation of these electron microstructures where you can nicely see where the active material particles are located, where the carbon, the binder, the pores are located, and so on and so forth. You need porosity also inside the electrodes, because you need a liquid electrolyte in order to ensure a proper lithium-ion exchange between the two electrodes that you have in a lithium-ion battery cell. Now let me dive into these different models describing each step of the manufacturing process, and the first one is the model simulating the slurry. Okay? So here we use an approach that we actually call coarse-grained particle dynamics. It's a kind of coarse-grained molecular dynamics at the particle level. Okay? Here, so we define two types of particles, the active material and also aggregates between carbon, binder, and solvent. Okay? representing in a simplified fashion the real complexity of a slurry, where you have already a problem of scales, because you have antimaterial particles which are extremely large, micrometer scale, and you have solvent molecules which are more than nanometer scale, right? Then you need to simplify your problem in order to simulate it. And then here in this model, so we describe interactions, as I was mentioning before, between the different type of components that you have in the slurry. The interaction between the antimaterial particles, that they can have different shapes, different sizes, and the interactions between these aggregates between carbon binder and solvent. Okay? Then we solve Newton-like equations, okay, by using some force fields describing interaction between the particles. And then, so based on these simulations, so we converge to an equilibrium state that will represent actually the virtual or digital twin of a slurry, right, that you have in there in periodic boundary conditions. And this digital twin of the slurry can be validated in terms of properties that we can measure experimentally, that you can calculate in the computer, and then with back and forth with the experiment, you can actually see if your calculations are correct or not. And if they are not correct, you will fit the force field parameters in order to match the microscopic properties of the slurry that you observe in the experiment. And here we deal with the density and the viscosity as a function of the applied shear rate. And you see here an example of comparison between the calculated viscosity as a function of shear rate for different solid contents and for two different formulations of the slurry, showing that the model works well. Okay. In order to fit the force fields, we use a collection of techniques. We use no equilibrium molecular dynamics in LAMS software. We use particle swarm optimization and also a bunch of machine learning techniques in order to accelerate the fitting of the force field parameters to match properly the microscopic properties of the slurry. This model here so provides a very useful information for industry. For instance, how the particles disperse in the slurry as a function of the particle size distribution of the antimaterial, as a function of the formulation, as a function of the solid content, which are all properties that are controlled at experimental level, right? And therefore, this gives information about rheology of the slurry. And this is something that industry needs to optimize properly in order to have beautiful coatings, to produce beautiful electrodes without cracks, for instance, right? High quality electrodes. Once you get this slurry simulated, you proceed further and you will simulate the drying. Okay? In order to simulate the drying, so what we do is we shrink the size of these aggregate particles, handling together the carbon, the binder, and the solvent, in order to mimic the fact that the solvent is going away. And then the microstructure converges to a new one that is going to represent actually the dry electron microstructure. This dry electron microstructure can be characterized in terms of a bunch of properties that can also be measured experimentally, for instance, the porosity, the electrical conductivity, and so on and so forth. And this model is also very useful because it can simulate different drying strategies. Okay? When you start, for instance, drying the slurry with high drying rate, then you go to low drying rate, or use more sophisticated protocols than this one. When you start with high drying rate, you go to low drying rate, and then high drying rate again. And then you can analyze how these drying protocols will impact the way that the materials will distribute in the thickness of the electron. And you can, for instance, very nicely capture a phenomenon called like CVD migration. CVD stands for carbon binder domain. So these are aggregates of carbon binder without solvent, because the solvent went away, because here you simulate the drying, so you don't have any more solvent. And this is a phenomenon that you want to avoid in the industry. You want to avoid that carbon binder go too much on the top of the electrode, because it will form an insulating layer and will then impede the electrical contact between the electrode and the, for instance, and the current collector, for instance. And this is something that, well, with this model you can actually analyze very nicely. And I'm not going to enter now into the details here to analyze the different curves and so on, but just sharing you the kind of things that this model can do. Then, so once you get this dry electron microstructure, so you will simulate the calendering. So here we press the electrodes, okay? Again, you need to do that in reality because you want to improve the electrical contact between the particles. Then, so you see in the simulation that you have some kind of elastic recovery here when you press the electrode, so the electrode then relax a little bit and recover a little bit the initial thickness, but not fully. This is a phenomenon also very well known in industry. This is the so-called spring-back phenomenon. And this happens because you have a polymer inside the electrode. You have a binder, basically. The role of the binder is sticking the particles to each other, but at the same time, this binder provides some elasticity. right? Well, the model is able to capture this kind of phenomena. Here we use discrete area method. We use as an input the dry electron microstructure. And then so here, this model captures also the impact of the calendering on the deformation of the active material particles that can eventually lead to cracking. It's something that also we want to avoid when we are producing these electrodes for battery applications. This is something that you can, the degree of deformation of the active material particles can be tracked using some descriptors, for instance, Hamming sphericity. When you are compressing the electrodes, the particles are becoming less spherical. Okay? And the nice thing with this model is it's 3D resolved, therefore you can compare the microstructures that you get from these simulations with reality. In particular, if you use images coming from computer tomography. You can have a one-to-one comparison between the virtually produced electron microstructures with the one that you get from the experiments. And you can then compare properties, for instance, the porosity of the real electrodes with the ones that you get from these simulations as a function of the compression degree. The amount of, the compression degree here refers to the degree of compression of electron versus initial thickness, right? 10% means that you are compressing 10% of initial thickness of the electron, and so on and so forth. And you see here very nice correlation also for other properties such as the tortuosity factor of the pores, okay? That will control the ionic conductivity of your lithium-ion battery electrodes. You can also extend further this model and track, for instance, the cracking. Okay, this is something that we have done inspired by some nanocomputer tomography experiments that we have performed. Where we observe that when you go very hard in terms of calendering conditions, when you apply very high pressures, the active material particles will start to crack. And this is something that you can capture in the model by extending this discrete element method by accounting by a bond breaking phenomena. Basically, the active material particles are defined as a collection of spherical primary particles. Then we track the mechanical stress between these spherical primary particles as a function of the applied pressure upon calendering. And then we can visualize and see where the cracks are going to happen. Right? Cracks are here represented in light blue. And you can even, along the calendering process, and you can even actually track what is going to happen in each individual active material particle. Here you see along the compression for the calendering how the number of bonds between the primary particles are disappearing, so are being destroyed. And you can actually, with this model, even identify differences in terms of degree of cracking for the active material particles which are closer to the calendering roll and the ones which are closer to the current collector. Okay? And you see that differences, and basically we found that the particles which are closer to the current collector will crack more than the particles which are closer to the roll, the calendering roll. Right? All this kind of information, again, is super useful for industry because they want to avoid this. Having cracks in active material particles is very bad for performance, right? And here you have a model that can give you insights. But still, this model is computationally expensive, okay? I'm saying this because you will see in a minute that with AI we can accelerate those things, right? We can basically mimic the behavior of these physics-based models much more quickly, right? The next step is the simulation of the electrolyte filling. Okay, once we produce these electrodes, you need actually to infiltrate the electrodes and the cells with a liquid electrolyte, which is needed in order to ensure proper lithium-ion exchange between the two electrodes in the cell. Here you see how fast is the filling. I will play these videos again. How fast is the filling of an alkaline electrode when the electrode is not compressed? Because yes, here the porosity is high, and the tortuosity of the pore network is very low. And how slow is the electrolyte filling for alkaline electrode? Okay. Here this happens because porosity here is lower, tortuosity is higher. You need actually, once again, to calendar electrodes in order to improve the electrical contact between the particles, but at the same time, so compressing about the electron means decreasing the porosity and therefore making more difficult the electrolyte filling, right? Well, the model here, which is based on lattice-Boltzmann method, so is capable to give insights regarding that. It's capable also to predict where the air is going to remain trapped inside the pores. Having air remaining in the pores is basically bad for a lithium-ion battery cell because your active material here needs to be fully exposed to liquid electrolytes. Okay, and this is something that you want to avoid. You want to avoid having air in contact with active material because then you will lose energy density and power density for your lithium-ion battery cell. Well, the model is capable to predict where exactly the air will remain trapped, right? To then provide some insights maybe on how to avoid this problem. And here you see an example of simulations. These are 3D simulations, but here I'm showing in 2D how the electrolyte infiltration looks like in cell sandwiches, where you have anode, cathode, and separator. Separator is a polymeric membrane with some porosity. You see that this process is highly heterogeneous, okay? And the reason is because the 2 electrodes here, they are made of different active material chemistries with different particle sizes. The electrodes, they have also different porosities, different tortuosities, like the separator. And therefore, this makes that the electrolyte infiltration is highly heterogeneous. That means that you will not fully fill all the pores with liquid electrolyte. And this is also a problem in industry. Okay? Industry wants to homogenize as much as possible the electrolyte infiltration of the cells, right? And this is something that is very hard, very time consuming. They spend up to 48 hours to try to optimize, in the production process electrolyte filling, and they're never sure that they're fully filling the cells with liquid electrolyte. Right? This tool can provide insights to help them to optimize faster this process step. And then we found other things that, for instance, you can predict some optimal electrolyte architectures to accelerate the infiltration process as well by using this tool. And last but not least, regarding this physical vein movements modeling part of the workflow, we have an electrochemical model. So a model simulating how the electrode will operate in a real cell and in connection to the electron microstructures predicted by our artistic manufacturing simulator. So here we put into this model the microstructures predict by using our manufacturing simulations, and then we simulate how they operate in a real cell. And we are able to, for instance, simulate observables that can typically be characterized at experimental level. For instance, galvanostatic discharge currents as function of applied C rate, which is more or less related to the current that you are requesting to the cell. As a function of the formulation of the electrode, that means the amount of active material that you have in your electrode, the amount of carbon binder that you have. As a function of the calendar in degree, the degree of compression. And here you see an excellent comparison between the predictions in black with the experiments, with the colors. Here we didn't change any parameter in the electrochemical model. The only thing we changed from case to case was the electron microstructure. Okay? That means that through the electrochemical observables, we can validate also our manufacturing simulator. Right? Because you find a good match between the performance descriptors of the electron microstructures with experimental ones, so you can say, okay, you can say, okay, I trust enough my model, my simulator of manufacturing, because we predict microstructures that then make sense electrochemically speaking. And this simulator also can provide insights on where the lithium is going to be intercalated in the active material in 3D. This is more like simulating operando experiments, right? In operando experiments for lithiation, the lithiation dynamics, okay? That will also very useful for industry because they can really see in 3D where the lithium will go as a function of the quality of the interfaces between active material, carbon binder, and pores, right? And then you can get other descriptors that I'm not going to comment now because it's of time. Now let's move to AI. Once you have all these sophisticated models, highly calibrated, validated with experimental data arising from the pipeline, so then we can start to play with AI. And the first paper, basically as far as we know, reported in the field of battery manufacturing using AI was a paper of my group. So it was published in December 2019, so we got cover from Batteries and Supercaps in January 2020. And you will see this application of AI is extremely simple, extremely simple, but it's still very useful, okay? And the take-home message here is that we don't need a lot of data to do cool things with AI, okay? And second, we don't need necessarily to use very sophisticated AI techniques. I mean, you can use simple things, even at experimental level, to maybe visualize your data in another fashion and then provide some useful guidelines to the technician or operator manufacturing lectures or manufacturing cells. The example here is regarding the application of a supervised machine learning technique called support vector machine, where we want actually to predict how the slurry formulation, that means the proportion of active material, carbon binder, you have in the slurry, the solid content of the slurry and the viscosity of the slurry impact the electroporosity produced with an active material. Here's nickel, manganese, cobalt, 111 in terms of stoichiometry between the three components. Here, so we produce a slurry, we cast it, and then we dry it, right? And then we measure the porosity, and we collect experimental data where we were reporting, for different formulations, I mean different percentage of active material per weight percentage of active material in the slurry. We were collecting the porosity as a function of the viscosity for different solid contents, okay? You see here a very messy cloud of points, right? Very messy cloud of points. We collect something like 80 conditions here, okay? It's not large. Each point was repeated, each experiment was repeated 5 times, okay? It's high quality. Machines produce high quality electrodes, right? Very reproducible electrodes. You have very small errors, right? The viscosity is linked to parameters that we can control in the coater, okay? The coma gap and the coater speed. Okay? I can comment later if you want about the meaning of this parameter more exactly, but these are parameters that can be controlled in machine level. Okay? That's why we are using viscosity here as one of the dimensions of this problem. By applying support vector machine, we actually convert this messy cloud of points in something that is more visible and more understandable. These are actually kind of, this is so-called boundary plots, which look more like phase diagrams, in solid-state chemistry. But this is not solid-state chemistry problem, this is manufacturing problem. And here, basically, what we can see is that it's impossible, according to this support vector machine output, to make electrodes with low porosity if you have a formulation of 92% of NMC. However, it becomes possible when you increase the formulation, the amount of active material in a slurry. You see these white zones appearing here. And then, so you can also, with this graph, if you are a technician producing battery electrodes, very quickly identify which viscosity you need, which solid content you need, and which formulation you need in order to make an electrode with low porosity, or to make an electrode with high porosity, if you like. Okay? Here, these labels, these classes, were defined by the human. Okay? Again, this is a very simple problem. So humans say, okay, if electrodes with less than 30% of porosity are low porosity electrodes. This is the first class. Second class is in between 30 and 40. Higher than 40 means high porous electrode. Okay? We didn't use any unsupervised technique here to identify the classes and so on. This was really human-based. Still, this revealed very useful. And nowadays, this model, at that time, this model has 80% of accuracy. That means that when you are performing, the model, you are entering the model some intended manufacturing parameters, like the intended formulation, solid content, and viscosity. The model will make a prediction that in 80% of cases revealed to be correct when you do the experiments afterwards. Nowadays, this model, 4 years later or 5 years later, it has an accuracy of 98%. Okay? Very simple model, which is being used, every day by our technicians in our pilot line. Very simple, right? But the take-home message here is that you don't need a lot of experimental conditions to do useful machine learning. What you need is high-quality data. Okay? High-quality data. You don't need to use super sophisticated AI techniques to get things that can be useful for experimentals when they are manufacturing electrode cells or materials. Then we extend these techniques for other experimental databases. For instance, we apply now more sophisticated pipelines combining, for instance, principal component analysis, unsupervised machine learning techniques, supervised machine learning techniques based once again support vector machine to predict which are the manufacturing parameter values that we need to adopt to improve the homogeneity of the electrodes being produced, but also to improve the calendering conditions, okay, to optimize the tortuosity of electrodes, the volumetric capacity, the energy density, and so on and so forth. Okay? A lot of problems that we have solved, thanks to AI that we have published very extensively. We have something like 25 papers on this. But now today I'm going to show with you one of our very latest papers. This was published a couple of weeks ago. We got also the cover in Advanced Energy Materials, which is a deep learning model of electrode calendering to make all these computations, of manufacturing simulations faster, to then pave the way towards optimization. And here, basically, what we have done is we have collected data arising from how the discrete element simulations of electrode calendering. We have voxelized these simulations of the electrode compression and the spin back. And then we use these images, which looks more like a time series, of images, to train a convolutional neural network model. And this convolutional neural network model is able now to simulate this calendaring process in a way much faster than what the original discrete method model is able to do. And here you see basically a comparison, so between the deep learning prediction with the discrete method simulation prediction of this calendaring process step. You see here a very good agreement in the time series for the volume occupied by the active material, the carbon binder domain, the void, which is actually all the space that you have on top of the electrode being compressed, and the pores inside the electrodes. So I will speak about accuracy here. Accuracy is something like 95%, okay, in terms of this time series prediction. And the advantage, once again, of this deep learning model is that it can actually simulate the calendaring process 200 times faster than what the high fidelity physics-based model can do. And therefore, this paves the way towards optimization, because you have a faster model, you can embed it, for instance, in a Bayesian optimizer, and optimize the calendaring conditions to reach your desired velocity, your desired conductivity, and maybe eventually to minimize the spin-back phenomenon. It's something that industry wants also to avoid. What is fantastic with this model is that when you get these final electron microstructures after simulating with the deep learning framework the calendaring process, you get the electrons with porosities, with diffusivities, tortuosities, conductivities, and so on, in good agreement, very good agreement with the ones that you get from the DEM simulation, despite that you didn't use these descriptors to train your convolutional neural network model. Okay? Your convolutional network model here was trained only with the time series of the compression. And this is amazing. This is amazing because it means that you can actually expend less time in training the model to get high accuracy results at the end of the day, because less time because you use less descriptors to train your model. Right? So this is something now that we are further extending for other process steps, for instance, the drying, right? And so on and so forth. This approach. Here you see another application of machine learning to exploit the data arising from these expensive computational simulations of the manufacturing process. This is for the electrolyte filling. For simulating the electrolyte filling, as I mentioned before, we were using the lattice-Boltzmann method. We have terabytes of data there from these simulations. These simulations are very expensive. It can take you up to 1 week to simulate the infiltration of an entire electron microstructure by using this method, lattice-Boltzmann method. So then we decide to use multi-layer perceptron models, I mean these more like neural network models, to exploit the data arising from these electrolyte infiltration simulations to make the same kind of simulations that lattice-Boltzmann method, but much faster, right, than lattice-Boltzmann method, thanks to this machine learning capability. And here basically now we can predict the infiltration in 3D of the electrodes with the liquid electrolyte in a few seconds instead of a few days, okay? Thanks to machine learning. And we can also basically simulate very good accuracy the saturation curves. Saturation here refers to the volume of pores occupied by liquid electrolyte divided by the total volume of pores occupied or not occupied by liquid electrolyte. In very good agreement with the prediction with the lattice-Boltzmann method model. So once you have this very fast simulator of electron infiltration, you can use it for high throughput screening. You can basically play with the electrolyte properties in terms of viscosity, in terms of density, in terms of contact angle, which are all properties that will impact the degree of infiltration of electrons by the liquid electrolyte. And you can perform a lot of simulations here, saturation curves, for different viscosity, different densities, different contact angles, therefore different electrolyte chemistries, to find basically the best electrolytes, the electrolytes that will actually accelerate this infiltration process, right? And then so you can establish, based on these simulations, partial correlation matrices, which are very useful to actually understand how these input parameters that you can control at experimental level will impact the electrolyte infiltration efficiency, right? For instance, here, so if I pick one example for a calendar electrode simulation using this machine learning framework. So yes, I mean, if I, for instance, increase the viscosity of my electrolyte, so I'm going to basically take more time to fill the electrode, right? And so on and so forth. And this is another example of application of machine learning to accelerate the physics-based simulations of the manufacturing process. This is for the electrochemical step, I mean for the very last step of the workflow. Here we exploit the data arising from our electrochemistry simulation. So we train also a convolutional neural network model which is able to simulate the lithiation dynamics of electrons in 3D by using as an input the microstructures arising from our manufacturing simulator of artistic, but again with the advantage that this can be done in a couple of seconds and not in a couple of hours or few hours of computational cost. Therefore, thanks to this tool, so you can simulate in 3D how the lithiation is going to happen in the electrode, how the electrochemical curve is going to look like, and therefore you can imagine now embedding this ultra-fast or high-speed tool in optimization, in the optimizer loop, to optimize the manufacturing conditions and then predict which manufacturing conditions you need to apply in order to optimize the energy density, for instance, of your electrode and your cell. Again, here I'm not discussing the details. I'm more interested to share the kind of things you can do with these tools, right? With AI in particular, to accelerate the optimization of battery manufacturing process. And now I'm going to speak at the end, so about this optimization, which closes the loop. Here we use in particular Bayesian optimization. We use this complex artistic manufacturing simulator to produce a lot of electromicrostructures that we have characterized in terms of properties, once again, porosity, thickness, composite, conductivity, and so on. We have derived then a machine learning model able to correlate the manufacturing parameter values that you want to apply and the properties that arise from these manufacturing parameter values. Here we explore 3 dimensions in this problem: the formulation of the slurry, the solid content of the slurry, and the compression degree in the Carinian step. And then we derive this model, machine learning model, which is now high speed. Okay, in a few seconds, give you responses, right? Okay, I apply these manufacturing parameters, then I get this electro property. We embed this high speed model now in a Bayesian optimizer to predict which manufacturing parameters we need to adopt to maximize or minimize thickness, porosity, and so on and so forth. Here you see a little bit the space of parameters that we have explored, how they look like. So we apply here Sobol sequences. I mean, it's a way of designing your design of virtual experiments. Okay. So we use these different synthetic conditions to run our manufacturing simulator, produce the synthetic data, and then train our machine learning model. You see here the performance of this, the accuracy of this machine learning model at predicting properties such as the tortuosity factor of electrodes, the conductivity, the active surface area, the density. When this number here is the actual score is close to 1, means that you have high accuracy model, high accurate model. Okay. Once this model is basically we are satisfied with accuracy, then we embed it in the Bayesian optimizer. And then so we can, thanks to this optimizer, predict which is the active material formulation, I mean the formulation you need to have, the solid content you need to have in the slurry, and the compression degree you need to apply in the Carinian step in order to, at the same time, maximize the electrode conductivity, maximize the electrode density, maximize the active surface area, which is the area of contact between active material and pore filled with electrolyte, and minimize the tortuosity, which makes the electron infiltration, more painful, right? And which decreases the ionic conductivity. That's why you want to minimize the tortuosity. This is a multi-objective optimization problem that can be solved thanks to the combination of these tools. And then so by embedding these manufacturing parameter values into our manufacturing simulator based on physics, and when we predict the electron microstructures thanks to this manufacturing simulator and we characterize the properties of these electrodes, we realize that the properties predicted match very well with the prediction arising from Bayesian optimization. This is a way of validating the outcome of the surrogate model based on machine learning plus Bayesian optimization. And then we perform experiments on top of that to validate further, the things, and we found that it was matching very well experimental data that we had. This is essential for realizing this digital twin process, because what you need for this digital twin, what you need to give autonomy to the machines to improve the process in autonomous fashion and so on, is a brain which works very quickly here. A brain which is able to process data very fast and gives responses, results very fast, instructions very fast to the machines. And this is something possible, again, thanks to this combination between physically informed surrogate models, Bayesian optimization. And this is something that we have extended also to account for electrochemical descriptors. That means that now in the tool you can say, okay, I want this power density, I want this energy density value for my cell, then the tool is able to predict which manufacturing parameter values you need to adopt in order to reach this desired target. And this is a dream now becoming a reality for industry applications. Right? Predicting recipes to adopt in terms of manufacturing to basically have the properties that you want for yourself. Right? That will be dictated by your application. To conclude, our artistic platform is doing physics-based simulations, calibrated based on data that we acquire in our pilot line. Having high-quality data is essential to develop this kind of models. Then we have a batch of AI models and tools that we have developed to treat experimental data, but also to treat synthetic data arising from our physics-based simulations to make them faster and to make actually solving these problems of multi-object optimization a reality. I mean, solving these problems, sorry for the redundancy, solving these kind of optimization problems. We account for the different steps. We go from powder to power, basically mixing, slurry, drying, calendaring, electrolyte filtration, electrochemical performance. All these models are interconnected with each other because this is what happens when you are manufacturing electrons and cells. So each step influences the others, okay, and so on. You need to account for this interplay between the different steps. And then to conclude, I would like to say a few words about education, which is also very important, I would say, in the field of AI, but also wider in terms of batteries, because right now we have something like 50 gigafactory projects running in Europe. Okay? That means that there are really a lot of needs in terms of manpower. And by next year, we estimate that we will need something like 800,000 new workers in the battery field to fulfill all these needs from these gigafactories. Right? We need skilled or upskilled people in this battery field. So what we are doing in my group since already almost 10 years, we are using digital tools to improve the training in battery field and also training machine learning aspects or simulation aspects in relation to batteries by using in particular mixed reality and virtual reality technology, right? But also some online platforms. And here I'm going to say a few words about that. We have an online platform called the Artistic Online Calculator, which is actually a platform that you can basically use for free. You can basically perform simulations using our physics-based simulators of the manufacturing process of lithium-ion battery electrodes and cells, from the slurry to the electrochemical simulations. So we have more than 1,300 users worldwide, 50% from industry. Not all these people is doing calculations, many people is just exploring the tool and so on. And this is good, this is great, because people get familiarized with simulation tools, the kind of things can be done and so on, retrieve data from the calculations, maybe to support their own research and so on. And here you see a video of one of our virtual reality tools that we have developed, which is a virtual reality digital twin of the pilot line that we have in our lab, which actually helps at explaining to general people, but also to students, how the pilot line works, the kind of parameters that you can play with, how these parameters impact the electrode, the quality of the electrons and the cells being produced, the interplay between the different parameters and so on and so forth. And here's what I want to say is that we have machine learning models inside, very simple machine learning models, regressions basically, because in the machines, in these virtual machines, you can, for instance, decide, okay, I want this calendar in degree, I want this calendar in temperature, or I want this dying rate. And then the electrode that will come out from this virtual reality simulator will have a corresponding porosity value predicted by the regressor, right? So it's a way of embedding machine learning models and make them useful to the wide public, even if they don't know there is machine learning inside. Okay? And here you see another example. This is mixed reality. You can use this by wearing HoloLens directly in the place of experimentation. So here basically you can interact with artistic simulator of manufacturing, and you can visualize the results like these electron microstructures directly in the lab, directly in the pilot line. And then you can see where the P-material is located, here in red, where the carbon binary domain is located, and so on, as a function of the applied manufacturing parameters. And therefore here the goal is really breaking the barrier between the digital and the real. We want to bring computations, we want to bring AI, we want to bring all these tools as concrete objects that people can manipulate in the real world. Okay? We don't want people to handle Excel files, computers, blah, 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 we want to centralize everything in the same space, right? And this is the direction that we're undertaking again since few years, right? That's why we are using this more and more this mixed reality tool. And last but not least, this is another application. This is actually a holographic notebook that we have developed, again in mixed reality. That allows, this is an operator of Tiamat, by the way, so who kindly help us at testing the tool and so on. Tiamat is a startup that we have created in the lab for producing sodium-ion batteries. And here in this holographic tool, the operator can basically inform with the data he's collecting when he's producing or she's producing an electrode or a cell. And then the holographic notebook gives feedback to the user, recommendations on how to optimize the process, how to optimize the formulation, how to optimize the drying rate, the calendar degree, directly in the place of experimentation, and thanks to the use of machine learning tools, again, regressors that we have developed in the artistic project. Once again, here is a demonstrator of our efforts to bring computational tools directly in the space of experimentation to break the barrier, once again, between digital and real. And this is my last slide. A lot of interest from industry on this, right? Batteries, manufacturing is really a blooming topic. Therefore, this pushes entering now in the world of business and so on. So we are basically creating a startup for this. We are developing a software that can be run from computers and from basically HoloLens glasses, being able to handle manufacturing data, performing simulations based on physics-based numerical models, forecasting with machine learning, solving these embedded design problems, predicting which manufacturing parameters you need to adopt to optimize the electrodes and the cells, and then providing also services for training. Super important in the battery field nowadays. Okay? Thank you very much again for the invitation and for your attention. Thank you.
Thank you for a impressive and comprehensive speech about digital twinning of battery manufacturer. It's quite impressive. I think we are a bit off time, but we have time for discussions. And this is an informal meeting, so I believe that everyone will excuse us if we extend a little bit, so there's no big problem about it. So, who wants to ask Alejandro something about this impressive work? It's so intense. Manuel.
Yeah. Thanks, Alejandro, for the talk. I wanted to ask about the active material you use in your models. Are basically inorganic ones. Have you also tried with organic active materials?
Excellent question. Yes, most of the active materials we have used are inorganic. For instance, NMC 111, 622. We have also used LFP. We have used graphite, silicon graphite blends, NCA, LTO, and so on. But we have actually used one organic material for sodium-ion batteries. This is a paper that we published in 2022. It's a material for sodium-ion batteries again that we synthesized in the lab. It's a material with very poor electronic conductivity, therefore you need to have a lot of carbon there. So that means the weight percentage of this active material is much lower, 60% more or less, much lower than what you will have with NMC. We are more always above 94 or something. Also aqueous, water and not NMP for the solvent. I didn't mention the chemistry of the solvent in purpose because of the audience, but it's better to have aqueous solvents because I'm environmentally more friendly than no aqueous, right? Organic and so on. Yes, we have published that, but it was the only tentative where we show that model works also. This, organic materials.
More questions? Go on.
Yeah, thank you very much again for this amazing talk. I was wondering, as much as you're able to design the material, are you able to then deconstruct it, for example, for recycling purposes and so on? Can you identify conditions that would weaken the binding? Are you able to, for example, delaminate the active material from the current connector and so on, that would facilitate recycling purposes as well?
Yes. So basically, it's also another problem that we have addressed. Here, I select some of them, right? And we have some papers actually in the pipeline not yet published, for instance, on the delamination problem. So that is actually demanding to study to optimize the drying conditions first Formulation, of course, will play a role there, because adhesion will improve if you have more binder. At the same time, if you have more binder, you increase the contact resistance between the electron and current collector. This is something that you want to minimize. You see, this is a very nice optimization problem. You want to maximize the adhesion, at the same time you want to minimize the contact resistance, right? So formulation plays a major role for that, drying as well, and calendaring as well, right? These are the 3 steps that we basically, the 3 things that we have considered in this optimization problem. Yeah, but we have actually addressed this problem as well. And then regarding, I think you mentioned recycling, right?
Yes,
Recycling, sure.
Open the active surface area to
yes. This is a topic that I have in the radar, okay, to maybe explore in the near future. You know, I'm coordinating an expert group, Deep Planet, so it's an expert group on digitalization in the Deep Planet network, which is a network dealing with pilot lines for battery production. And now, so the hot topic there is recycling digitalization, how we can use digital tools to support the recycling of battery materials and battery electrodes and so on. And we start to think and brainstorm which tools can be implemented and used for that. For now, it's not a topic that I have addressed personally, right? But there are a lot of opportunities there. I think that with optimization of these manufacturing conditions, you can already give some, insights for recycling people, right? To improve the recycling efficiency, I would say. But we didn't address this topic yet, directly. So,
thank you very much.
So well.
I think we can have just one more, but we have plenty of time then the coffee breaks to continue the discussions. Anybody wants? I'll have just one, if I may.
Yeah, sure.
In your input, you're dealing with raw materials, and raw materials are variables, so they have variable characteristics. I did not see in your presentation characteristics of those raw materials, for example, particle size, particle shape, for example. How do you deal with that? How do you cope with that? How do you insert that in your...
Sure. So the input of this workflow is definitely the particle size distribution of your active material. So this is something that you get from, for instance, the provider of your active material. But of course, we always double check with microscopy SEM, for instance. We perform SEM characterization of the powder, and we see more or less if the size of the particles match what the provider is telling us. Exactly. And then the shapes. The shapes actually we extract them by using computer tomography. So basically we use computer tomography of the electrodes, okay? So if you use microcomputer tomography, you will not see the carbon and binder. It is impossible to see, but however you will see very well where the active material particles are located. And then you can see very well the shapes of these active material particles. So then what we do is we extract these shapes, and then so we reconstruct the shapes in the computer by using a collection of spherical primary particles that we embed in the real shapes. And then we apply our force fields and so on to simulate the slurry, drying, carrying. Yeah. Yes, exactly. So the model can use real data or imagined data. I mean, people can imagine a shape or a size and then see what happens in terms of manufacturing efficiency. The two things are possible. Yeah.
All right, great. Well, thanks. I think
Thank you.
And now I thank Alejandro